Every seasoned comet specialist agrees on one unsettling truth. 3. I-Atlas is not acting like anything humanity has ever catalogued in the night sky. As this interstellar nomad hurtles toward its October approach with Mars, it has begun to cloak itself in a luminous emerald shroud. An atmosphere so vast it now stretches beyond the girth of mighty Jupiter. Its brilliance erupts in unpredictable surges. Its tail twists against the very principles of solar physics, and its drifting dust reflects sunlight in patterns no instrument has ever recorded. With each passing day and each step closer to the red world, its presence feels less like a natural traveler and more like something engineered. Yet the strangest detail remains hushed. While amateur stargazers across the globe share tentative images of this celestial enigma, the great eyes of Space Hubble, James Webb, Gemini have fallen curiously silent since August. Stay with me until the very end of this nocturnal inquiry, as we uncover why 3i Atlas defies the cosmos and why silence now veils what may be the most extraordinary celestial drama of the 21st century. Part 1. A comet that refuses to behave. In mid-September of the year 2025, something unfolded in the heavens that astronomers had not anticipated. The interstellar traveler known as 3i Atlas brightened far more rapidly than the carefully built models had forecast. Right as it drew to a distance of about 2 astronomical units from the Sun, the question that now grips the scientific community is deceptively simple yet deeply unsettling. Why? To grasp the scale of this puzzle, it helps to understand what astronomers mean by a predicted light curve. In human terms, imagine it as a kind of celestial weather report. But instead of forecasting rain or sunshine, it projects exactly how luminous a comet should become as it nears the Sun. These predictions are not idle guesses. They emerge from decades of study, built on refined models of how ice sublimates in the void of space and how dust grains scatter starlight. For many weeks, 3i Atlas behaved exactly as those models prescribed. Professional astronomers and dedicated amateurs around the globe tracked its slow but steady increase in brightness as it journeyed inward from the far reaches of the solar system. Each measurement fit perfectly. The comet's glow intensified in predictable fashion as its surface warmed, releasing jets of vapor and dust that built up its familiar, hazy atmosphere. Then, between September 7th and 15th, the script changed. Observers recorded brightness values that soared beyond the expected line. In astronomical terms, 3i Atlas had jumped its lane, and the deviation was anything but subtle on the standard magnitude scale used to chart brightness. The comet's light curve veered decisively away from its forecasted track. It was as if a car cruising at steady speed had suddenly felt someone press the accelerator to the floor. Yet the mystery only thickened. Within the astronomical community, debate ignited. Was this truly an explosive outburst of cometary activity, or merely the result of something more technical? The so-called aperture effect. This concept refers to how different telescope sizes and observational techniques can inflate or diminish apparent brightness. Imagine standing at a distance from a campfire. If you peer through a narrow tube, you may notice only the central flames, bright and compact, and conclude the blaze is small but fierce. Open your view wide, and suddenly the glowing embers and faint flickering spread far beyond that core. Different telescopes, each with their own apertures and methods, can produce similarly divergent impressions of a comet's broad, diffuse atmosphere. The most widely consulted public records are hosted by the Comet Observation Database, or COBS. Its charts, viewed at a glance, reveal the telltale moment in mid-September when the upward slope of 3I Atlas steepened dramatically. The line's change is impossible to miss, though interpretations vary sharply. To appreciate the sheer dynamics at play, consider the comet's speed as it hurtles sunward. 3I Atlas is traveling at tens of kilometers per second, which translates to over 210,000 kilometers per hour, fast enough to span an entire continent in less than a minute. Near perihelion, the point of closest approach to the Sun. Predictions suggest it will accelerate to about 68 kilometers per second. The calculations are precise. Perihelion is expected in late October, between the 29th and 30th, at a distance of roughly 1:36 to 1:4 astronomical units. That puts it just inside the orbit of Mars, and indeed, Mars itself plays a role in this unfolding drama. On October 3rd, 3I Atlas will swing past the red planet, coming within about 0.19 astronomical units. This approach has drawn the focused attention of mission planners overseeing spacecraft in Martian orbit. Instruments such as the High-Resolution Imaging Science Experiment, or HiRISE, the Color and Stereo Surface Imaging System, or CASIS, and the High-Resolution Stereo Camera, HRSC, all intend to seize this chance for opportunistic observation of an interstellar visitor passing close by. So what does it all mean? In plain language, there are a few possibilities. Perhaps 3I Atlas is shedding gas and dust more vigorously than any model dared to predict. Or perhaps the vastness of its atmosphere is tricking our instruments into readings that overstate the surge. Or, most unsettling of all, both factors may be happening at once. The consequences of this are not trivial. This object represents only the third confirmed interstellar body ever witnessed crossing into our solar system. Unlike the familiar comets that spring from the Kuiper Belt or the Oort cloud, looping predictably around our Sun, 3I Atlas hails from somewhere else entirely. Its strange behavior is therefore a priceless window into the chemistry and physics of alien systems. And yet, here it is, defying the rules we thought were universal. Its brightening anomaly forces us to ask, are we overlooking some fundamental principle of cometary dynamics? Do interstellar objects play by laws that differ from the ones written into the story of our local comets? The timing makes the mystery all the more dramatic, as 3I Atlas nears its closest passage to the Sun. Virtually every telescope on Earth and in orbit is bracing to scrutinize it. The findings that emerge in the weeks to come may not simply add a footnote to astronomy, but reshape our understanding of what populates the spaces between stars. And yet, the surge in brightness is only the opening act of this enigma. The cloud of gas and dust surrounding the comet's hidden nucleus is swelling to dimensions that defy ordinary physics, expanding more quickly than the textbooks say is possible. Part 2. Growing faster than physics. The strange behavior of 3I Atlas cannot be reduced simply to its sudden brightening. The hazy veil surrounding it, the coma is expanding at a pace that unsettles our most basic understanding of cometary physics. To see why this matters, one must first understand what astronomers mean by a coma. Imagine it as a comet's atmosphere, but one unlike the Earth's tidy, gravitationally bound shell of air. A comet's atmosphere is chaotic, unconfined, and perpetually changing, a turbulent cloud of gas, dust, and plasma stretching for hundreds of thousands of kilometers. When surface ice warms and sublimates, leaping directly from solid to gas, it drags dust into space, creating a diffuse envelope so vast that it can rival planets in scale. On the 6th of August, 2025, the James Webb Space Telescope turned its infrared instruments on 3.1 Atlas and revealed something extraordinary. Its coma contained an unusually high abundance of carbon dioxide relative to water vapor, a ratio extreme even by cometry standards. This pointed to an origin in a region of its native star system far colder than the birthplaces of most known comets, or to a chemical history unlike anything familiar within our own solar neighborhood. The carbon dioxide dominance carries profound implications, whereas water ice requires strong sunlight to sublimate. Carbon dioxide begins its transition much farther from the sun. This means 3I Atlas awakened earlier in its inbound journey, coming alive and venting gas long before ordinary comets would stir. Spectroscopy confirmed this awakening, revealing an enormous carbon dioxide-dominated shroud stretching hundreds of thousands of kilometers. Some estimates place its scale at nearly 700,000 kilometers, half the diameter of the Sun. Yet this figure remains provisional, since different observing techniques yield different values, and consensus has not yet formed. A few weeks earlier, on the 21st of July, the Hubble Space Telescope provided another piece of the puzzle. Its images revealed that the nucleus was completely smothered within a brilliant cocoon of dust. By applying brightness models, astronomers constrained the radius of the nucleus to no more than about 2.8 kilometers, contradicting exaggerated claims circulating on social media and in some sensational headlines. Independent support came from the Vera Rubin Observatory's Legacy Survey of Space and Time, whose June images suggested a nucleus just a few kilometers across. Reports citing diameters from 3 to 5.6 kilometers reflect the range of uncertainty, but the prevailing conclusion is that the nucleus is small rather than monstrous. Understanding the nature of this colossal envelope requires a grasp of dusty plasma, a blend of neutral dust grains and gases, some of which have been ionized by solar radiation. This medium does not behave like ordinary matter. It arranges itself into filaments, curtains, and structures that seem to ripple with life. Observers who describe seeing organic patterns in the coma are witnessing plasma self-organization, driven by magnetic fields threading the ionized gas and creating invisible lanes for charged particles. The physics is akin to the aurora shimmering above Earth's poles, or to the vast loops of plasma arching from the Sun's surface. What makes 3I Atlas so perplexing is the combination of traits: a rapidly growing coma, rich in carbon dioxide, swelling far beyond expectation, has never before been recorded in an interstellar object. The first visitor, Vienci Oumuamua, displayed no cometary activity at all. The second, Dvastiborisov, looked much like a conventional comet of our solar system. 3I Atlas stands between these extremes. unmistakably cometary yet chemically alien. The strange blend of carbon dioxide dominance, rapid envelope expansion, and erratic brightening points to an object that resists our categories. Even the speed of the coma's growth forces unsettling questions. Based on the sunlight it now receives and the known sublimation rates of familiar ices, the coma should be expanding at a steady, predictable rate. Instead, it appears to be inflating more rapidly, as though an unseen energy source is at work. Could radioactive decay within its core be adding heat? Unlikely. Given the nucleus's modest size, might rapid rotation be fracturing the surface and exposing new ice layers? Conceivable, though unproven. Or is its chemistry infused with exotic volatiles that Earth-based experience has never prepared us to anticipate? The plasma only deepens the puzzle as the relentless solar wind collides with the vast coma. It creates a bow shock, an invisible wavefront, not unlike the wake spreading behind a ship cutting through water. This interplay between solar wind and plasma accelerates the swelling of the coma and sculpts it into delicate, thread-like forms, giving the comet an appearance that feels strangely alive. And yet, even when these plasma effects are taken into account, the rate of expansion remains unusually high. It is as though 3I Atlas is governed by a rulebook entirely separate from the comets astronomers have charted for centuries. The dominance of carbon dioxide chemistry may help to explain part of this mystery, but it does not complete the puzzle. With each step inward toward the solar heart, this interstellar wanderer provokes more questions than it resolves. The growing envelope continues to balloon outward, driven by volatile ices that should not be so vigorous at its present distance from the sun. But the expansion is not the only enigma. Through the long nights of summer, astronomers detected a transformation even more uncanny. The coma's color began to shift, radiating a spectral green glow worthy of science fiction itself. Part 3. The green glow. Under the clear, unpolluted skies of Namibia. During the eclipse nights, between September 7th and 17th, amateur astronomers captured images that stunned even seasoned stargazers. Their cameras revealed 3I Atlas glowing with a vivid green radiance, a hue so intense it seemed almost artificial against the star-dappled canvas of space. While green comets are not unknown to astronomy, the science behind the glow follows a well-established process. It occurs when molecules of diatomic carbon, two carbon atoms bound together, are struck by the sun's ultraviolet light. These molecules absorb high-energy photons and then re-emit that energy as visible light, concentrated at a wavelength of about 518 nanometers, which the human eye perceives as green. Ordinarily, this phenomenon follows a predictable rhythm. As a comet nears the sun, the rising heat fractures complex carbon-bearing compounds within the nucleus, releasing diatomic carbon that fuels the emerald glow. The brightness of the fluorescence scales directly with the amount of carbon-rich material in the comet and the intensity of solar radiation it absorbs. Yet in the case of 3I Atlas, the rules appear unsettled. Early spectroscopic data indicated that the comet contained unusually high levels of carbon dioxide, but showed little evidence of the classic carbon chemistry that typically produces such glowing emissions. In theory, that composition should have delayed or weakened the appearance of green coloration. Instead, the opposite happened. The comet began shining green earlier than expected, and with surprising strength. defying predictions based on its distance from the Sun or its carbon dioxide-dominated chemistry. Scientists describe this as startling and continue to probe the anomaly. To appreciate why, it is helpful to consider the delicate dance of chemistry unfolding within the coma. As solar light warms the nucleus, different volatiles sublimate at different thresholds. Water ice demands intense heating. Carbon dioxide transitions earlier, and complex carbon molecules fracture in stages as the temperature rises. A bright green glow implies that carbon-bearing molecules are breaking apart and fluorescing sooner, or more efficiently, than models would suggest. It is as if 3I Atlas holds carbon chemistry unfamiliar to us, or that solar heating is acting upon its ices in ways unaccounted for. One possibility is that the comet's evolving chemistry is shifting faster than expected. As the body draws nearer to the Sun, previously stable compounds may decompose, producing new molecules that fluoresce at visible wavelengths. The green light could thus be a signature of a chemical transition occurring more rapidly or broadly than usual. It is essential to clarify that the nucleus itself is not green. The solid core of 3I Atlas likely resembles other cometary bodies, a dark, rocky amalgam of ice and dust, often tinged red or brown. The emerald glow originates entirely in the surrounding atmosphere, a gas and dust envelope extending for thousands of kilometers into space. This distinction is crucial when linking the green fluorescence with the earlier brightening anomaly. If the coma is swelling in density, while carbon-bearing molecules accumulate in greater numbers, then the intensity of green light would naturally rise as well. The two phenomena may reflect different aspects of the same deeper process. Think of it like a neon sign flaring to life when current surges through it. The green aura of 3I Atlas may be signaling that its inner chemistry is awakening more vigorously than models predicted. With solar energy unlocking reactions in dramatic fashion, yet caution must temper these interpretations. Digital cameras and image processing can exaggerate colors beyond what the human eye perceives directly. The striking green images circulating online may appear bolder than what one would actually glimpse through a telescope eyepiece. Even so, the spectral line at 518 nanometers is indisputable evidence. Diatomic carbon is fluorescing in the coma. The glow may even reveal insights into the comet's spin and hidden architecture. A rapidly rotating nucleus would sequentially expose different surface regions to sunlight, altering how the green emissions wax and wane, and potentially shaping subtle patterns in their distribution. Some observers have noted shifts in both the brightness and the reach of the green glow over spans of mere hours or days, a hint that the nucleus of 3I Atlas may indeed be rotating. Yet, beyond the data, the psychological effect of such a spectacle is profound. Across human history, strange lights in the heavens have stirred equal parts awe and dread. A comet shining emerald, especially one that has drifted from another star system, inevitably calls to mind the alien and the otherworldly. Centuries of storytelling and modern science fiction have conditioned us to link green illumination with futuristic technology or extraterrestrial presence. And yet, the lesson of astronomy is humbling. The cosmos consistently crafts displays more mysterious and spectacular than even the boldest imagination of fiction writers. The glow of 3I Atlas, though unusual in its timing and intensity, arises from authentic chemistry, molecules broken apart and re-energized by solar light, under the unforgiving conditions of deep space. This comet is nothing less than a natural laboratory, carrying frozen matter from a distant system now awakened by the sun's radiation. As it approaches perihelion, the emerald aura is likely to grow even more intense. Increasing solar energy will fracture additional carbon-bearing molecules, potentially yielding scenes of even greater drama. Around the globe, amateur astronomers keep their instruments trained on the comet, recording its transformations and providing invaluable data to professionals piecing together the puzzle of this interstellar visitor. The green fluorescence is but one element of its bizarre character, yet it stands as the most visually arresting, paired with the rapid expansion of the coma and the puzzling brightening anomalies. It reinforces the impression of a comet that refuses to behave like any other. And yet, even this alien-seeming glow may be overshadowed by another enigma, one rooted in geometry. Astronomers are now focused on the orientation of 3I Atlas's tail, a feature that appears to resist the fundamental physics governing how a comet's tail should respond to the solar wind. Part 4. The anti-tail and odd geometry. In the standard framework of comet science, tails always extend away from the sun, acting like vast cosmic windsocks shaped by the relentless forces of radiation pressure and the charged particles streaming outward in the solar wind. This principle has held true for every comet humans have tracked, from ancient returns of Halley's Comet to the dazzling apparitions of recent decades until 3.1. Atlas seemed determined to bend the rules. To understand why this departure matters, one must revisit the physics of ordinary tail formation. As a comet nears the sun, radiation pressure pushes dust grains outward, curving them into a sweeping dust tail that arcs along the orbital track. At the same time, the solar wind, rushing outward at hundreds of kilometers per second, ionizes molecules in the coma and drives them into a straight, bluish ion tail pointing directly away from the sun. Together, these two features create the archetypal cometary image etched into our imagination. The physics is straightforward. Particles and plasma flow along the paths of least resistance under the sun's dominance. But with 3I Atlas, early observers noticed something uncanny: a plume directed sunward, an apparent anti-tail. Instead of streaming away from the star, material seemed to be thrust toward it, as if the comet were resisting both sunlight and the solar wind. Before invoking exotic forces, anti-gravity, or alien engines, it is crucial to recall that anti-tails, though rare and dramatic, have natural explanations. They emerge from perspective and geometry. Picture a thin sheet of dust spread through space. From Earth, if our line of sight cuts edge-on through that sheet, part of it may project against the sky in such a way that it looks like material is streaming toward the sun. In reality, nothing is breaking physical law. It is a visual illusion crafted by viewing angle. The geometry becomes trickier still once 3I Atlas's orbit is considered. The comet traces a nearly retrograde path inclined by about 5 degrees to the ecliptic, the broad plane of planetary orbits. This unusual tilt amplifies the potential for peculiar projections. Later imaging, including a striking capture from the Gemini South Telescope on August 27th, showed a conventional anti-solar tail pointing outward as expected. But the earlier sunward spike had already fueled speculation about 3I Atlas's strange behavior. polarimetric studies added further complexity. By examining how scattered light waves were polarized as they bounced off the comet's dust, astronomers found evidence for structured, organized distributions of matter patterns not captured by the simple models used to describe most comets. The data suggested a coma architecture more intricate than a smooth haze, more akin to folds and ridges, like the difference between an inflated balloon and an origami sculpture. The anti-tail, combined with the comet's high velocity and tilted orbit, created a spectacle that stirred both public fascination and professional curiosity. To casual observers, it seemed as though the comet was rebelling against the forces that govern celestial bodies, and when nature appears to rebel, the imagination leaps to extraordinary explanations. Was this truly a comet? Or something propelled by its own power? Yet, as so often in astronomy, the reality is subtler but no less captivating. The anti-tail is the product of the same geometric tricks that shape optical illusions on Earth. Just as a straight road may appear to bend at the horizon, or distant mountains can seem to hover when light bends through the atmosphere, the apparent sunward spike of 3I Atlas arises from natural causes. Its shallow orbital tilt against the ecliptic only heightens these effects, ensuring that as it passes through three-dimensional space, different slices of its dust and gas shroud reveal themselves in shifting, sometimes misleading ways to the eyes of those watching from Earth. What seems to be a tail pointing straight at the sun may in fact be streams of dust and gas moving in many directions, with only certain portions aligned to our perspective. To make sense of the anti-tail, one must think in 3 dimensions while studying images flattened into 2. It is like watching shifting shadows cast on a wall and trying to reconstruct the shape, depth, and angle of the unseen objects that create them. The shadows are real, but interpreting them requires geometry. As 3I Atlas presses closer to perihelion, its anti-tail will almost certainly change. Altered viewing angles will reveal new portions of its vast atmosphere or conceal others, producing fresh optical puzzles. The central task for astronomers is separating true physical anomalies from illusions born of perspective. In this respect, the anti-tail is a perfect emblem of the comet itself. It looks alien, yet its behavior remains bound by natural laws. Its strangeness is magnified by geometry layered atop authentic chemical and physical peculiarities. Still, perspective effects, striking as they are, cannot rival what comes next. For there is one property of 3I Atlas that has moved scientists beyond curiosity into astonishment. The way this comet polarizes light, how it alters the orientation of the very waves themselves, reveals features that resist comparison with any comet ever studied in our solar system, or any object yet known from interstellar space. Part 5. A swarm in the skies. The autumn skies of 2025 have taken on the look of a cosmic traffic jam. Multiple luminous comets are sweeping through the inner solar system at the same time, weaving a celestial display unmatched in decades. At the very heart of this gathering, 3I Atlas blazes its singular path, a messenger from another star system framed by a supporting cast of homegrown comets. The timing has produced a rare convergence of events. Comet R2 Swan reached perihelion on September 12th and will make its closest pass to Earth around October 21st, drawing within about 0.25 astronomical units roughly 23 million miles. At that range, it may well brighten enough to be visible to the naked eye beneath dark skies. Another player, Comet 414p gedeeld door St. a periodic visitor, completing a circuit every 7.5 years, reached perihelion on September 27th at about 0.52 astronomical units, first discovered by NASA's Solar Terrestrial Relations Observatory. This comet adds another gleaming thread to the tapestry of the season. Perhaps most dramatic of all is Comet A6 Lemon, predicted to reach magnitude 3 to 4 at its peak. It will graze perihelion on November 8th at a distance of 0.53 astronomical units, promising a spectacle bright enough to pierce even moderately light-polluted skies. To understand why so many comets appear at once without being linked, imagine cars converging on a city by separate highways. The comets trace independent orbital paths, but happen to pass through the inner solar system in the same broad window of time. Their clustering is an illusion of timing, not kinship. The visibility of comets depends on distance, on how large their comas and tails grow near the sun, and on whether they traverse patches of sky dark enough for observers. The simultaneous presence of several bright comets is a statistical fluke of orbital mechanics, not a cosmic conspiracy. Yet the swarm of autumn comets is only part of the sky's story. Mid-September also delivered a cascade of asteroid encounters, sparking headlines and social media chatter about near-Earth objects. The most prominent was the pass of asteroid 2025 FA22 on September 18th. Harmless though it was, crossing millions of kilometers away, its flyby drew intense coverage. The name alone, 2025, was enough to fuse public imagination with the concurrent cometary activity. Several smaller asteroids slipped past during the same span, each one brief fodder for news feeds. The clustering of these events magnified the impression that September 2025 had become a uniquely turbulent chapter in Earth's cosmic encounters. The reality is simpler. Asteroids routinely pass close to Earth, but only the most conspicuous are noted. What is new is the vigilance of modern surveys, which detect more objects than ever before. The heightened sense of activity reflects our sharpened vision, not an actual surge in celestial traffic. Still, the psychological weight of so many events compressed into a short interval is unmistakable. Humans are wired to seek patterns, and when multiple celestial phenomena unfold together, the mind instinctively looks for meaning. For millennia, strange alignments of comets, planets, and stars have been read as omens of fate. The present abundance, comets and asteroids both, naturally rekindles that ancient impulse. For those inclined towards speculation, the timing provokes tantalizing ideas. If an advanced intelligence sought to send reconnaissance craft into our solar system, might they choose to mask their presence among a natural surge of comets? Such camouflage would be ingenious. A swarm of comets provides cover, making artificial interlopers indistinguishable amid the natural crowd and less likely to attract scrutiny. Periodic bursts of comet activity already occur, triggered by gravitational nudges in the outer system that funnel icy bodies sunward in groups. An artificial visitor slipping in alongside them would be hidden in plain sight. The speculation grows richer when one considers which orbital pathways might best serve such a covert mission. raising questions that blur the boundary between science and imagination, a trajectory that threads past multiple planets, like the course carved by 3I Atlas, would grant a traveler the chance to survey several worlds in a single passage. Its close brush with Mars offers opportunities for detailed observation before the comet plunges deeper toward its rendezvous with the Sun. From a strategic standpoint, the timing could not be more advantageous for concealment. The skies are already crowded with bright visitors, creating a natural curtain of activity. With the public's gaze fixed on comets and asteroids, any anomaly risks being dismissed as just another point of light in a busy firmament. Yet the simpler explanation is almost certainly the correct one. Gravitational nudges in the outer solar system periodically dispatch clusters of comets inward, their arrivals overlapping to form swarms, such as the one we see now. Likewise, the asteroid flybys that peppered September are routine encounters, long part of Earth's neighborhood but newly recognized thanks to improved detection. Still, 3I Atlas remains the outlier, among them carrying the unmistakable mark of an interstellar origin and flaunting characteristics no ordinary comet has displayed. The distinction raises an unsettling possibility. Are we watching coincidence at work, or a pattern with intent behind it? That question grows sharper in light of one final observation, an empirical detail that refuses to fit neatly into existing models. The sunlight reflected from 3I Atlas is polarized in ways that diverge from anything recorded before. Its light waves emerge rotated, ordered, and shaped in manners that standard cometary physics struggles to explain. For some scientists, this behavior represents the most confounding clue of all. Evidence that the comet's very structure may be unlike any object humanity has studied, whether native to our solar system or adrift from beyond. Part 6. Natural or artificial? The central question troubling astronomy in 2025 is no longer whether 3I Atlas is unusual on that point. There is universal agreement. The deeper question is whether its strangeness reflects natural processes we have yet to grasp, or whether it signals something that challenges our very assumptions about what can exist in interstellar space. To appreciate the stakes, we must revisit the two earlier interstellar wanderers that crossed our skies. The first, Oumuamua, discovered in October 2017, overturned expectations by refusing to behave like a comet at all. Though its hyperbolic orbit made clear that it originated beyond our solar system, it showed no visible coma or tail. Instead, it tumbled silently through space like a shard of rock. More asteroid than comet, even more bewildering. Oumuamua displayed a faint but measurable acceleration not attributable to gravity. That unexplained push ignited fierce debate. Some argued for exotic possibilities, residual outgassing from hidden ices, or even propulsion of artificial design. The idea of a derelict spacecraft was raised, if only because conventional cometary physics fell short of explaining the anomaly. 2 years later, 2I Borisov offered a striking contrast. Discovered in August 2019, it behaved precisely as textbooks predicted. Borisov bloomed with a bright coma and sweeping tail as it neared the Sun. Spectroscopy revealed a chemistry broadly similar to local comets, suggesting that the processes that form such icy bodies may be universal across stellar nurseries. Now enters 3I Atlas, a traveler that sits between these poles. It exhibits obvious cometary traits. Yet its chemical mix, polarization patterns, and rapid atmospheric expansion defy the neat categories established by Oumuamua and Borisov. Among the most critical puzzles is its nucleus size. Data from the Hubble Space Telescope constrain the radius to roughly 2 optkilometers, placing its diameter below 5 kilometers. Ground-based surveys agree, estimating only a few kilometers across. This is far smaller than the 50-kilometer giant speculated in early reports. Such a modest body poses a severe problem. How can so little material generate the vast, expanding coma that now surrounds the comet? Unless its ices are sublimating with extraordinary efficiency, or its composition contains volatiles more potent than those of ordinary comets. The physics do not add up. It is this tension that fuels the appeal of artificial explanations. If 3I Atlas is too small, too active, and too chemically exotic to fit the mold, might it not be a comet at all? Yet science resists such leaps until every natural possibility has been tested. Occam's razor counsels that the simplest explanation accounting for all observations is most likely true. Before invoking alien engineering, astronomers exhaust every terrestrial mechanism. And possibilities do exist, an unusually volatile rich chemistry, perhaps seeded in a colder region of its birth system, could explain both the early onset of activity and the carbon dioxide dominance. A fractured surface texture might allow sunlight to penetrate deeper, releasing gas more efficiently. Rapid rotation could create centrifugal stresses, flinging material into space. Internal cracking might expose fresh reservoirs of ice to solar heat. Each factor could magnify the apparent output of a small nucleus. Yet the polarimetric data remain especially compelling. When sunlight reflects from dust grains, the orientation of the light waves carries subtle fingerprints of the particle's size, structure, and composition. Measuring polarization is like decoding a hidden message written into light itself. The readings from 3I Atlas are unprecedented. They do not align with any comet, asteroid, or planetary dust cloud previously studied. In that polarization, strange, structured, and unaccounted for lies perhaps the most direct evidence that 3I Atlas is not just another icy wanderer, but something fundamentally different. An emissary from interstellar realms carrying mysteries we have only begun to confront. The extreme negative polarization values measured for 3I Atlas reaching a minimum near -2.7% at phase angles around 7 degrees stand as unprecedented results, defying current theories of how dust grains scatter light. Such anomalies hint at unusual properties within the dust itself. Alterations caused by irradiation over a vast interstellar journey. Exotic chemistries, unknown among solar system bodies. Or even materials with optical traits, unlike anything typically produced in nature. Commentary from respected researchers, shared through academic blogs and preprint archives, acknowledges the authenticity of these findings while urging caution in their interpretation. The data are real, and they pose a serious puzzle. But extraordinary claims demand extraordinary proof. The idea of an artificial origin, while tempting, faces steep obstacles. No radio emissions have been detected from 3I Atlas despite targeted searches by multiple observatories. There is no evidence of course corrections, no telltale maneuvers that would suggest active control. Its orbit, though unusual, remains firmly within the bounds of gravitational dynamics and requires no resort to exotic propulsion. And if it were artificial, the implications border on the staggering. A journey from another star system at plausible spacecraft velocities would require thousands, even tens of thousands of years. Any civilization capable of mounting such a mission would command technologies so far beyond our comprehension that they verge on myth. By contrast, the natural explanation, though demanding revisions to cometary physics and interstellar chemistry, requires no leap into the realm of alien engineering. 3. Atlas stretches the limits of what we thought possible for natural bodies. But it has not yet crossed into the territory where artificial origins are the only viable answer. As fresh data accumulate, the scientific community will inch toward consensus. The process may take months or years, but eventually the balance of evidence will tilt, either toward exotic yet natural processes or towards something more extraordinary, and the stakes are immense. Were 3I Atlas ever proven to be artificial? It would mark humanity's first confirmed encounter with technology from another star system, an event that would permanently alter our conception of our place in the galaxy. But before vaulting to such conclusions, another possibility deserves attention. What if 3I Atlas is not a solitary traveler at all, but a shard of something greater? Imagine a massive debris field hurled across interstellar space by some ancient catastrophe. In that context, 3I Atlas, and perhaps the other strange objects recently glimpsed in our skies, could be fragments of a long-ago disaster, remnants of a cosmic event so violent it scattered its wreckage between the stars. Sometimes, the most extraordinary mysteries are born not from deliberate design, but from the aftermath of unimaginable destruction. Part 7. The debris field hypothesis. Sometimes, the most extraordinary explanations arise from the most catastrophic origins. One possibility is that 3I Atlas, together with other strange visitors now appearing in our skies, is not a lone wanderer at all, but a shard of debris from a cosmic disaster that took place thousands or even millions of years ago in a distant stellar system. The implications stretch imagination while remaining grounded in known physics. Several mechanisms exist by which material can be expelled into interstellar space at speeds sufficient to carry it across the gulfs between stars. Planetary formation itself is among the most violent epochs of any system's history. When worlds collide, fragment, and hurl smaller bodies into the void. Our own solar system bears scars of such events, with the prevailing theory holding that Earth's moon was born from the impact of a Mars-sized body with the proto-Earth. Stellar flybys offer another ejection mechanism. When two systems brush past one another, gravitational tides can strip objects from their original orbits, casting them outward on interstellar trajectories. Simulations suggest these encounters are not rare, but recur throughout galactic time, seeding a continual population of wandering fragments. More dramatic still is the total breakup of planets or moons, whether triggered by tidal stresses during close stellar encounters, internal instabilities such as runaway heating, or even technological catastrophes on a planetary scale. Such events would scatter shells of debris outward, expanding across interstellar space at enormous velocity The chemistry of 3I Atlas hints at such an origin. Its unusual abundance of carbon dioxide suggests it formed under extremely cold conditions, perhaps in the far outskirts of another star system where carbon dioxide ice could endure for geological ages. Material expelled before undergoing the usual thermal processing of planetary formation would retain this volatile-rich signature. The comet's reddish, spectral slope provides another clue. Such coloration could arise from prolonged bombardment by cosmic rays during a long interstellar passage, or it might preserve the imprint of formation conditions unlike anything in our solar system. The red hues echo the surfaces of trans-Neptunian objects that have been weathered for eons by radiation. Even the polarization anomalies may lend weight to the debris field hypothesis. If the dust of 3I Atlas was forged in a violent ejection, or altered by ages of exposure to interstellar radiation, its grains might scatter light in unfamiliar ways, producing optical signatures never seen in local comets. Exotic textures could emerge from shock processing during a catastrophic expulsion or from slow modification under galactic cosmic rays. Still, temporal clustering in Earth's skies is not proof of common origin. The seeming coincidence of several unusual objects arriving in the same era could be explained by observational bias coupled with new technologies. Sky surveys today can detect faint interstellar bodies that would have passed unnoticed only a decade ago. The timing also coincides with solar maximum in 2025, when heightened solar activity amplifies interactions between comets and the solar wind, making marginal objects more spectacular and newsworthy. Yet, if 3I Atlas truly belongs to a broader debris field, then more fragments may yet reveal themselves. In the years ahead, we may find additional interstellar wanderers, each carrying the fingerprints of an ancient catastrophe written into their chemistry, structure, and light. The Vera Rubin Observatory's legacy survey of space and time promises to revolutionize our view of the skies, dramatically expanding our ability to detect faint, fast-moving objects and perhaps uncovering a hidden population of interstellar travelers that have long slipped through unnoticed. Within this context, the debris field hypothesis becomes more compelling. Picture fragments hurled into space by a catastrophic event as confetti flung from a speeding car. At first, the pieces move together in a tight stream, but across millennia, gravitational pulls from passing stars and the drag of interstellar material spread the fragments across ever-widening volumes of space. Detecting them today would be like trying to pick out individual sparks from a firework that exploded thousands of miles away. Long after the flash had faded, such debris would reach us at staggered times and from varied directions, making their shared origin almost impossible to recognize without deep chemical and dynamical investigation. What kind of evidence would lend weight to this hypothesis? If multiple interstellar objects revealed unusual chemical fingerprints not seen in our solar system, yet consistent among themselves, that would be persuasive. Likewise, if their velocities and trajectories could be traced back toward a common point of origin, the case would grow stronger. Computer models simulating the dispersal of debris from different types of cosmic disasters could further test the theory. Should these simulations reproduce the arrival patterns and compositions we now observe, the debris field explanation would gain real credibility. The timescales involved border on incomprehensible. Suppose 3I Atlas emerged from a violent disruption 10,000 years ago in a system 50 light-years distant. It would have been crossing interstellar space, since before human beings cultivated crops. Born in an age when our ancestors still roamed as hunter-gatherers, oblivious to the fact that cosmic shrapnel was already en route to their far-off descendants. From this vantage, the debris field idea offers a middle path between exotic natural processes and artificial origins. It requires no alien machinery, no violations of physics, no secret knowledge, only the acknowledgement that our galaxy is more violent and chaotic than the relative calm of our present solar system suggests. The implications stretch far beyond 3I Atlas. If interstellar debris fields are common, they represent natural laboratories for exploring how planets form elsewhere. Each shard would carry records of the conditions and chemistry of its home system, preserving data from events that shaped worlds beyond our reach. Yet catastrophic debris is not the only lens through which to view coordinated arrivals. Another possibility lingers at the edge of speculation. What if 3I Atlas and its strange companions are not chance fragments at all, but scouts deliberately dispatched by a distant civilization probes hidden in plain sight, moving among natural comets, quietly surveying a solar system that has finally begun to notice them? Part 8. The Scout Theory. In 1960, mathematician and physicist Decadesago, the engineer Ronald Bracewell, proposed an idea that continues to haunt the search for extraterrestrial intelligence. Rather than broadcasting fragile radio signals across vast galactic distances, he suggested that advanced civilizations might send autonomous messenger probes, scouts, dispatched to nearby star systems. These machines, unlike beams of radiation, could gather detailed knowledge of alien worlds up close. The rationale is persuasive. Radio emissions fade with distance, their strength diminishing according to the inverse square law, making interstellar communication across thousands of light-years inefficient. A physical probe, by contrast, could travel at sublight speeds, arrive in a target system, and conduct direct surveys with sensors and instruments that no remote signal could match. Building on Bracewell's foundation, mathematician John von Neumann described a related vision: self-replicating machines, Suchdevices, capable of harvesting local materials to build copies of themselves, could in theory multiply across the galaxy. Combined with Bracewell's concept, von Neumann probes might spread exponentially, each new generation leaping from one star system to the next. Over millions of years, they could seed the Milky Way with a silent, enduring network of watchers. The Scout Theory, applied to 3I Atlas, forces us to ask whether this interstellar visitor could be one such probe, an emissary disguised as a comet. The brilliance of such a strategy lies in camouflage. A machine masquerading as a comet could pass undetected, its orbit governed by celestial mechanics, while quietly studying each planet along its trajectory. The path of 3I Atlas carries it near Mars, then inward toward Venus and Earth. A course idéal for reconnaissance. The timing, arriving during a period of heightened solar activity, might even serve a purpose: to observe how our civilization's technologies withstand space weather, power grids, satellite links, and communication systems all betray their strengths and weaknesses when buffeted by solar storms. Some of 3I Atlas's most puzzling traits could be reinterpreted under this lens. Its erratic brightness could be more than mere outgassing. It might represent modulated signals, data relays, or system tests disguised as natural variability. The rapid expansion of its coma could reflect the controlled release of gases used to unfurl sensor arrays or antennas, maintaining the illusion of cometary behavior while serving engineering needs. Even its chemistry raise questions. Carbon dioxide, unusually dominant in its spectrum, could have been chosen deliberately. It functions as a convenient propellant, enabling small attitude adjustments while cloaking them beneath a natural veil. To outside observers, such maneuvers would appear indistinguishable from standard sublimation. The anti-tail geometry, puzzling when interpreted as natural, could likewise serve a hidden purpose. While geometry explains the effect to astronomers, it would also maximize solar collection if panels were aligned sunward, drawing energy in a configuration that doubles as a cometary illusion. The polarization anomalies may be the most tantalizing clue of all. Natural dust grains have never yielded polarization values like those recorded from 3I Atlas. Artificial materials, engineered for durability or optical specialization, might produce precisely such anomalies. A probe crossing interstellar space would need shielding against radiation, micrometeoroid impacts, and temperature extremes. Advanced composites or exotic coatings could easily display optical properties foreign to natural dust. The comet's compact nucleus fits this hypothesis as well. A reconnaissance probe need not be massive. Miniaturization, even by human standards, allows instruments of great sophistication to fit within packages smaller than satellites. For a civilization far beyond ours, cramming advanced systems into a body only a few kilometers wide, or disguising machinery beneath a thin layer of dust and ice, would be entirely plausible. Yet the scout theory carries weighty challenges. No artificial transmissions have been detected, despite extensive monitoring by radio telescopes worldwide. The object shows no unambiguous signs of course corrections or deliberate maneuvers. Its trajectory, while odd, conforms to gravitational dynamics without requiring exotic propulsion. The technological hurdles also loom large. A probe would need to survive millennia adrift in the hostile environment of interstellar space, withstanding cosmic rays and interstellar dust impacts, while keeping systems intact across unfathomable timescales. Upon arrival, it would have to execute complex operations with flawless reliability. Such feats demand engineering far beyond anything humanity can conceive. Moreover, if such civilizations exist, they may already have the means to detect us from afar. Our radio leakage has been spilling into space for nearly a century. A species capable of interstellar missions would hardly require a hidden comet to confirm our existence. Why dispatch probes to spy close up when technology advanced enough to build them could likely analyze us across light years? The scout theory, then, remains a provocative lens, one that ignites imagination while underscoring the limits of our understanding. The scout hypothesis also forces us to grapple with deeper questions of motive and timing. Why, if such probes exist, would an advanced civilization select this precise moment in human history to send them? After all, our own technological footprint, the radio waves and emissions leaking into space, has been detectable for less than a century. The blink of an eye in cosmic time, that a probe would appear during humanity's short adolescence of technology feels strikingly convenient. Even so, the unusual properties of 3I Atlas, coupled with its timing, provide a narrative that is difficult to dismiss outright. If we ourselves were tasked with designing a reconnaissance mission across interstellar space, many of its observed traits would align with engineering logic. A disguised probe could study Earth's atmosphere, magnetic shield, and technological systems while masquerading as a harmless comet, its scientific observations indistinguishable from natural phenomena, its trajectory, sweeping past multiple planets, maximizes the return on the colossal investment of time and energy demanded by interstellar travel. More provocative still is the possibility that 3I Atlas is not solitary. The cluster of strange objects visible in recent months could, under this view, represent a coordinated survey, multiple scouts gathering data from different vantage points at once. And yet this suggestion drives us to a deeper paradox. If the galaxy truly hosts civilizations capable of sending such probes, why has humanity never encountered definitive proof of their existence before now? Why has the universe remained silent, despite the scale of time and opportunity? In confronting this puzzle, we arrive at one of the most enduring enigmas in science, a riddle that has haunted astronomers and philosophers alike for generations. Part 9. Fermi Paradox Meets the Sky. In the summer of 1950, during a casual lunch at Los Alamos National Laboratory, physicist Enrico Fermi voiced a question that has haunted both science and philosophy ever since. Where is everybody? With those three words, he exposed a paradox that remains unresolved to this day: the striking mismatch between the apparent likelihood of extraterrestrial civilizations and the persistent silence of the skies. A decade later, astronomer Frank Drake attempted to quantify this contradiction. In 1961, he introduced what became known as the Drake equation, a framework that multiplies together factors such as the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, and the probabilities that life arises, develops intelligence, and achieves technology, even with conservative inputs. The equation suggests our galaxy should host thousands, perhaps millions of civilizations capable of communication. With 400 billion stars in the Milky Way and billions of years available for life to evolve, the absence of alien visitors feels, statistically, almost impossible. This tension between probability and evidence is what we now call the Fermi paradox. Interstellar bodies like 3I Atlas feed directly into this debate, refining some of the variables in the Drake equation. The discovery of thousands of exoplanets has already demonstrated that planetary formation is common. Likewise, the detection of interstellar comets and asteroids proves that young systems undergo violent scattering events, flinging debris into the void between stars. Each fragment carries with it chemical fingerprints, unique clues to the environments and histories of its parent system. 3I Atlas, rich in carbon dioxide, may have formed in the frozen outskirts of its origin star. In regions cold enough for carbon dioxide ice to endure for geological ages, such conditions are not rare, implying that the building blocks of life could be distributed widely across the galaxy. If advanced civilizations do exist, interstellar objects could serve them as perfect camouflage. A probe hidden among natural comets would be nearly indistinguishable. especially during swarms when multiple bright bodies compete for attention. The autumn skies of 2025 create exactly such a stage. From this perspective, one possible resolution of the Fermi paradox is unsettling in its simplicity. Perhaps alien visitors are already here, but they prefer quiet reconnaissance to theatrical displays of power. Rather than risk alarming or provoking emerging species, they might gather intelligence discreetly, ensuring they remain unseen. The Scout hypothesis fits neatly within this framework. Civilizations might be rare, but not non-existent. If even a tiny fraction of star systems produce technological societies, the galaxy's immensity and antiquity would still allow for the occasional dispatch of interstellar reconnaissance missions. Yet the caution of science must prevail. Natural explanations remain strong contenders for the anomalies of 3-1 Atlas. Its unusual mix of volatiles, its rapidly expanding coma, and its extreme polarization values could all stem from natural processes shaped by a unique formation history or structural complexity. The clustering of comets and asteroids in the autumn of 2025 may be nothing more than the product of improved surveys and observational bias. What once passed unnoticed now fills our databases, creating the illusion of an extraordinary alignment. Scientific discipline requires that we pursue every natural explanation before invoking the extraordinary. The guiding principle of Occam's razor reminds us that the simplest hypothesis, the one demanding the fewest assumptions, is most often correct. Exotic natural phenomena extend our physics. Artificial probes demand an alien technology far beyond our reach. Still, the parallels remain difficult to ignore. If reconnaissance probes from other civilizations do exist, their operational design would match uncannily well with many of the very features that make 3I Atlas so strange. Long-duration missions through interstellar space would demand robust systems, machines engineered for endurance rather than elegance, designed to survive millennia amid radiation, dust impacts, and cold. Stealth would favor designs that blend seamlessly with natural phenomena, allowing reconnaissance to unfold under the guise of ordinary cometary behavior. Yet the question of timing remains the most troubling flaw in the Scout hypothesis. Why would alien probes arrive precisely during humanity's brief technological adolescence? Our radio leakage has been detectable for less than a century, our satellites for only a few decades. The odds of first contact aligning with this narrow sliver of history seem improbably convenient. One possible resolution is to imagine that reconnaissance is routine. Advanced civilizations may dispatch probes at regular intervals, regardless of whether a system shows clear signs of technology. In this view, arrivals follow statistical rhythms, not the development status of the inhabitants. Another possibility is that our signatures are louder than we think. High-energy bursts from nuclear weapons tests, radar emissions sweeping the skies, and the constant pulse of satellite communications may be visible across much greater distances than we typically assume. From this perspective, 3I Atlas might represent a response to decades of unmistakable signals, proof that Earth has entered its technological era. The search for extraterrestrial intelligence has long emphasized radio astronomy, straining to detect messages across the void, yet perhaps physical scouts are more common than distant transmissions. A cautious civilization might prefer direct observation to broadcasting signals that could expose them. If so, we have been looking in the wrong way. listening when we should have been watching. The mystery of 3I Atlas will not resolve overnight. Future data will decide whether it belongs to the catalogue of natural wonders, its exotic behavior illuminating new chapters in planetary science, or whether it carries the fingerprints of engineering. Either outcome reshapes our view of the universe. If natural, it testifies to a galaxy far more violent and chaotic than the relative calm of our solar system. If artificial, it reveals intelligence on scales that dwarf human capacity, civilizations subtle enough to hide in plain sight while gathering what they need. In that possibility lies perhaps the most profound resolution of the Fermi paradox. They are here, but careful, quiet, and deliberate. Their presence revealed not by messages shouted across the stars, but by the faint, enigmatic behavior of a comet named 3I Atlas. Part 10. Alien Invasion or Cosmic Coincidence. As 3I Atlas presses on toward the inner solar system, astronomy finds itself entertaining debates that would have sounded implausible only a short time ago. The evidence is incomplete, yet persistent enough that serious researchers are now openly considering scenarios that stretch beyond the safety of conventional models. On one side of the argument stand comet specialists with decades of accumulated knowledge. Their view grounds itself in natural explanations. The unusual brightening, they argue, stems from exotic volatile ices reacting to sunlight in ways our models have not yet mastered. The anti-tail geometry emerges from perspective our line of sight, intersecting a complex three-dimensional dust sheet. Even the comet's extreme polarization values, so unlike anything seen in solar system objects, might still reflect natural dust properties forged under alien conditions. To them, the principle remains clear: extraordinary claims demand extraordinary evidence. And 3-1. Atlas has not yet crossed that threshold. Its chemistry, its rapid coma expansion, its odd scattering of light, all could plausibly result from a comet that formed in the frigid outskirts of a foreign star system, shaped by histories unlike anything in our backyard. On the other side grows a chorus, less convinced by coincidence. The timing of arrivals in autumn 2025, the clustering of brilliant comets, and a spate of asteroid flybys creates the impression of design. The anti-tail's geometry, the comet's emerald glow, and its ballooning coma combine into a spectacle that seems almost calculated to seize attention. Conspiracy-leaning interpretations seize on these alignments, arguing that such synchronicity is too precise to dismiss as chance. The mid-September asteroid passages, paired with the comet's eerie behavior, weave neatly into a story that invites talk of orchestration. Yet through it all one fact remains reassuring. 3I Atlas poses no threat to Earth. Its closest approach will occur on December 19th. At 1.8 astronomical units, about 170 million kilometers. That distance is greater than the span separating Earth from the Sun. Its path will indeed carry it by Mars, Venus, and even Jupiter, but always at millions of kilometers remove. Whether natural or artificial, there is no mechanism by which this comet could menace our planet. Still, the allure of exotic explanations is easy to grasp. The green aura, the contrarian tail, the inexplicable brightening, all mirror imagery long cultivated by science fiction, imagery that primes us, to equate strangeness with alien craft. Our cultural training predisposes us to dramatic conclusions, to imagine visitors heralded by unmistakable signals or dazzling technologies, yet reality may unfold in subtler ways. Reconnaissance designed to avoid provoking alarm might look exactly like this: ambiguous, fascinating, but never definitive. From that perspective, the very debate unfolding now could be the intended outcome, a wave of scientific attention and public curiosity without the destabilizing shock of certainty. Ambiguity permits study while delaying the social upheaval that proof might unleash. Timing, however, continues to divide interpreters. Advocates of natural causes insist that improved detection methods and greater public interest explain the clustering. The skies have always been busy, they argue. We are simply better at noticing. Advocates of more exotic interpretations counter that the convergence is too neat. Interstellar visitors are rare. Systematic surveys are recent. And yet multiple anomalies crowd the skies precisely during humanity's fragile technological adolescence. The probability, they suggest, strange. For now, professional astronomers tread carefully in public, guarding neutrality. Yet in private conversations, even seasoned researchers admit that 3-1 Atlas is pressing the limits of what their science has seen before. The polarization data stands apart as perhaps the most provocative measurement of all values, unlike any previously recorded from a natural body. To reconcile them, astronomers must either stretch existing theories of light scattering or confront the possibility of something more exotic. Institutional responses, however, have remained markedly cautious. Major observatories and agencies have confined themselves to technical reports, carefully avoiding speculation about broader meaning. This restraint is as much about scientific discipline as it is about pragmatism. Speculation carries risks, not least the prospect of public overreaction to extraordinary claims. Yet the silence has consequences. The absence of fresh, high-resolution imagery from the flagship space telescopes throughout September has left a void, and into that void conspiracy theories have rushed, while scheduling demands, maintenance cycles, and operational constraints offer reasonable explanations for the delay. The timing appears suspiciously convenient to those predisposed to dramatic interpretations. The issue of disclosure looms unavoidably. If 3I Atlas does represent something beyond natural physics, how would the world's institutions handle such a revelation? The social consequences could be seismic religious upheaval, economic instability, shifts in geopolitics, even the reordering of humanity's self-image. In this light, a strategy of gradual acclimatization may be the wisest course. By letting debates unfold in public view, society is allowed to entertain possibilities once dismissed as unthinkable, adjusting incrementally rather than facing a single shattering announcement. The stakes grow with every kilometer the comet closes. As 3I Atlas nears perihelion in late October, each observation carries the potential to tilt consensus either toward extraordinary but natural cometary behavior, or toward the unprecedented recognition of alien technology. Nothing less than humanity's cosmic identity hangs in the balance. Perhaps this is simply a comet from another star, displaying physics at the edge of our models. Or perhaps it is evidence that we are not alone. and that others possess both the will and the means to study us across the gulf of light years. Yet one question now gnaws at those following its progress most closely. Where are the detailed images that should, by now, be streaming from our most powerful space-based telescopes? Part 11. Where are the images? The timeline of 3-1 Atlas observations contains a curious silence, one that has unsettled both professional astronomers and conspiracy-minded onlookers. Around the world, amateurs continue to post striking photographs of the comet's green-shaded coma and its defiant tail geometry. Yet the great observatories in space, which should be delivering the clearest images and the most detailed spectra, have fallen oddly quiet during the pivotal month of September. Hubble's last publicly released images date to July 21st. Those snapshots, crisp and luminous, showed a compact nucleus engulfed in a glittering dust cocoon, helping establish the comet's size and providing critical baselines for its unusual traits. But as of September 22nd, no new Hubble images have appeared, despite the comet's rapid brightening and its increasingly theatrical display. James Webb's contribution came on August 6th, when its spectrometers revealed the carbon dioxide, rich chemistry that set 3I Atlas apart from any comet yet studied. The discovery made global headlines, firmly placing the object in a category of its own. And then, silence. No September data. No updates in the public archives. Gemini South gave the public one dazzling glimpse, a high-resolution image of the comet's tangled tails that captivated audiences and circulated widely online. But even that masterpiece was captured on August 27th and released a week later again. A record of August, not September. Under normal circumstances, few would question such delays. Large observatories operate under heavy scheduling pressure, with observation slots requested months or years ahead. Technical constraints compound the challenge. As 3I Atlas approaches superior conjunction, moving closer to the sun's glare from Earth's perspective, telescope operators face limits on how close they dare point their instruments. Solar elongation rules protect delicate optics from catastrophic damage. Add to that the standard proprietary periods, which grant research teams exclusive access to their hard-won data, and the processing pipelines that require weeks of careful calibration before images can be released. And the lag becomes understandable. Oversubscription makes it worse. Hubble, Webb, and their peers are flooded with proposals, and every observation must compete with countless other worthy targets. And yet, the timing gnaws at the imagination. September was the very moment when 3-1 Atlas began its strangest performance, the sudden brightening that defied prediction curves, the green fluorescence that burned brighter and earlier than models allowed. For those inclined towards suspicion, this is exactly when authorities might lock down information. If something truly extraordinary were glimpsed, might governments or international consortia withhold the data? Citing security or social stability, the absence of fresh imagery fuels the suspicion that suppression, not scheduling, explains the silence. Meanwhile, amateur astronomers have rushed to fill the vacuum. From Namibia, Chile, and Australia, their cameras have caught the comet's evolving face, its glow, its restless transformations. These images, stitched together from clear dark skies, form a global chronicle of September. But however stunning, they cannot substitute for the forensic precision of professional spectroscopy or the calibrated eyes of billion-dollar telescopes. The void remains, and with it, the uncomfortable question, why now? Of all times, have our most powerful instruments gone quiet? The contrast between a flood of amateur images and the silence of professional archives has created a strikingly uneven information landscape. Social media brims with vivid photographs of 3I Atlas, its green-tinged coma, its layered and shifting tails, yet the official repositories that usually anchor such events remain sparse. In this void, amateur astronomers have stepped into an unexpectedly central role, using sophisticated backyard observatories and coordinated global networks. They have documented the comet's changing brightness and morphology with remarkable consistency. In some cases, their temporal coverage surpasses that of major surveys. Still, no matter how impressive, amateur contribution cannot replace professional data. High-resolution imaging, calibrated photometry, and precise spectroscopy remain indispensable for deciphering the comet's chemistry, nucleus structure, and true physical behavior. These are the measurements only space-based facilities can deliver, and their absence grows more conspicuous as the comet enters its most dramatic phase. September should have been the critical month. This was when the anomalous brightening accelerated, when the green fluorescence intensified, and when shifts in the anti-tail geometry might have revealed new details about the comet's dust distribution. Yet in the public record, September remains largely blank. The gap lands precisely at the moment when the object's behavior became most scientifically intriguing, an omission that feels almost scripted to invite speculation about hidden findings. Normally, international astronomy thrives on shared access. Even if public release lags, preliminary data often circulates through professional networks. The fact that no such whispers have surfaced suggests either that observations were not made, or that access is being restricted more tightly than usual. The upcoming superior conjunction, when the comet passes behind the Sun from Earth's vantage, provides a natural reason why October will see reduced opportunities. But this does not explain September, when elongation remained sufficient for safe operations, and the comet was ideally placed for study. The Mars flyby on October 3rd now stands as the last prime opportunity for high-resolution imaging before the conjunction closes the window. Several spacecraft in Martian orbit are preparing opportunistic campaigns to observe the encounter, potentially capturing perspectives unavailable from Earth. After conjunction, in late October and November, 3I Atlas will reappear in the dawn sky, once again within reach of telescopes on Earth. That reemergence may finally reveal how its coma, nucleus, and chemistry have evolved under the stress of solar heating at perihelion. Yet the lingering question remains, will post-conjunction data fill the gaps, or were the most crucial details recorded and withheld during September's silence? For now, astronomers wait with unprecedented anticipation, knowing that the next set of images could clarify the comet's true nature or deepen the enigma. Meanwhile, a darker interpretation circulates among the public. Superior conjunction, they say, offers the perfect blind spot. The choreography of October 2025 looks to some like the ideal stage for concealment, a moment when nature itself conspires to shield the comet from scrutiny. To astronomers, It is simply an unfortunate but predictable limitation of orbital mechanics. To others, it is the very definition of a cosmic cover-up. Superior conjunction, the period when 3I Atlas passes behind the Sun as seen from Earth, will cloak the comet in solar brilliance precisely as it enters its most active phase. In astronomical terms, superior conjunction occurs when an object slips to the far side of the Sun relative to Earth's perspective. At that alignment, the Sun's overpowering glare swallows the object completely, creating a natural blind spot in our surveillance of the inner solar system. For 3I Atlas, the alignment is exacting. Its closest approach to the Sun, its perihelion, coincides almost perfectly with this observational blackout. The mathematics of orbital mechanics dictates this outcome. On October 21st, the calendar delivers both a new moon and the moment of minimum solar elongation for 3I Atlas. The comet drifts too close to the Sun's position in the sky, disappearing in daylight brilliance. For ground-based telescopes, it becomes invisible. For space-based observatories, it becomes dangerous. Sensitive optics and detectors risk catastrophic damage when pointed too near the Sun. Engineers impose strict safety margins, typically preventing instruments from observing targets within 15 to 30 degrees of solar proximity. Depending on their design and wavelength regime, these are not arbitrary rules, but necessary protections for billion-dollar assets. Even if the instruments could safely look, the signal-to-noise ratio collapses near conjunction. Against the searing backdrop of solar light, the faint glow of 3I Atlas would vanish, like trying to photograph a candle flame while staring into a floodlight. From a scientific standpoint, the blackout is inevitable. From a conspiratorial one, it looks almost too perfect. If someone wished to suppress evidence of extraordinary activity, they could ask for no better cover than this. Just as the comet should reach its most spectacular display, it will vanish from Earth's view. Perihelion arrives Oktober 49. The moment when comets usually erupt into their greatest activity, shedding gas and dust in torrents. Yet 3I Atlas will spend this entire period hidden in conjunction's glare. By the time it re-emerges into the pre-dawn skies of late November, the show will be waning. The peak already passed. Still, conjunction does not erase the comet entirely. A fleet of spacecraft occupies vantage points beyond Earth's line of sight, offering opportunities to monitor the event despite the blackout. The Solar and Heliospheric Observatory, or SOHO, routinely images the near-Sun environment and could capture glimpses of 3I Atlas during its passage. NASA's Solar Terrestrial Relations Observatory, or STEREO, deploys 2 spacecraft ahead of and behind Earth in its orbit, providing unique viewing angles clear of solar interference. The European Space Agency's Solar Orbiter, on its tilted elliptical path, offers yet another vantage point, rising above the plane of the planets to study the Sun and potentially the comet from perspectives unavailable to Earth. Meanwhile, October 3rd offers one last prime opportunity as 3I Atlas sweeps past Mars. Several orbiters circling the red planet are preparing opportunistic campaigns to study the encounter. Their instruments may deliver close-range data on the comet's coma and nucleus, filling part of the gap before the conjunction curtain falls. The final clear window before conjunction falls to Mars. Instruments circling the red planet are uniquely placed to capture 3I Atlas at close range. The high-resolution imaging science experiment aboard Mars Reconnaissance Orbiter, the color and stereo surface imaging system on the European ExoMars Trace Gas Orbiter, and the high-resolution stereo camera on Mars Express all possess the precision needed for cometary study. Together, they offer the last chance for high-quality imaging before the sun's glare hides the comet from Earth altogether. The data they collect on nuclear structure, coma chemistry, and tail dynamics will provide perspectives unavailable to even the largest Earth-based telescopes. In today's interconnected scientific world, such results rarely remain hidden for long. Agencies and research teams maintain active data-sharing pipelines and social media channels that usually release notable images within days or weeks. Should these Mars-based instruments record anything extraordinary, whether unexpected structures or chemical oddities, their findings will almost certainly find their way into the public domain. The timing of this encounter is further complicated by the Sun itself. Conjunction arrives as the star nears its maximum in the 11-year solar cycle. Flares, coronal mass ejections, and intensifying solar wind buffet the inner solar system, often reshaping cometary tails. Entire ion tails have been known to snap away during these events, producing sudden and spectacular changes in brightness. For 3I Atlas, such natural fireworks could easily mask or mimic artificial signatures, blurring the line between comet physics and something stranger. If an artificial system were hidden within its icy frame, the turmoil of solar maximum would provide perfect camouflage, concealing emissions or maneuvers beneath the background noise of solar storms. Everything, then, depends on what emerges from the sun's shadow. Guides predict that in late November the comet will reappear in the pre-dawn skies, visible from both hemispheres. Its appearance at that moment may prove decisive. Should it return with unexpected brightness, altered tail geometry, or behaviors inconsistent with post-perihelion norms, the case for exotic interpretations would strengthen. If instead it re-emerges, looking like an ordinary comet past its prime, its activity waning, its light curve fading, then the natural explanation will stand reinforced. December 19th marks the next key date. On that day, 3I Atlas makes its closest approach to Earth. Still a safe one, 8 astronomical units away, but near enough for the best post-conjunction scrutiny. By then, several weeks will have passed since perihelion. Enough time for the comet to clear the solar glare and once more fall under the gaze of major observatories. Plans are already in motion. Amateur communities worldwide are coordinating observation campaigns, building data-sharing protocols, and preparing to supplement official efforts should institutional access remain limited. Their global network, flexible and tireless, will ensure no detail escapes record. Thus, the conjunction period becomes more than a technical inconvenience. It is also a test of transparency. How governments, agencies, and international consortia handle the blackout will reveal much about their priorities and about what they choose to share. If 3I Atlas is merely another comet, the silence will soon lift with a flood of new data. But if it conceals something extraordinary, the conjunction provides an ideal pause, a curtain behind which analysis can unfold, unseen and unanswered. Advanced spacecraft with specialized sensors may yet observe 3I Atlas during the conjunction blackout, their data withheld until governments decide what, if anything, should be disclosed. The precedent is well established. In military and intelligence domains, sensitive information often remains classified for years or decades. The same transition could occur here, from open scientific discovery to a matter of national security. Should the comet display characteristics that demand official attention, from a more optimistic viewpoint, the blackout may be nothing more than unfortunate timing, robbing the public of a rare chance to witness one of the most intriguing astronomical events of our age. When 3I Atlas re-emerges in late November, it could usher in a new era of understanding, offering unprecedented insights into interstellar objects and the conditions that shape them. Superior conjunction thus becomes a mirror for human psychology. To skeptics, it is a routine celestial alignment. To conspiracy theorists, it looks like the perfect opportunity for secrets to be hidden. And in the liminal space between those perspectives, ambiguity thrives. The situation carries an uncanny echo of science fiction. Many observers have noted its resemblance to a satirical film that warned about precisely this kind of crisis. The 2021 Netflix production Don't Look Up presented a darkly comic parable in which warnings of an incoming comet are dismissed, distorted, and monetized until it is too late to act. Intended as satire on climate change denial and political dysfunction, the film now feels uncomfortably prophetic to those following the 3I Atlas debate. In the film, astronomers identify a comet on a collision course with Earth, but their urgent pleas are drowned out by political theater and celebrity distraction. Officials manipulate information for advantage. Billionaires propose profit-driven schemes that worsen the crisis. And the media packages apocalypse as entertainment. The resonance with 3I Atlas lies not in physical danger. The comet poses none but in the social response to uncertainty. Here, too, astronomers detect something unusual, an interstellar body displaying behaviors that strain conventional models. And here, too, their findings are filtered through bureaucratic channels and media lenses that often dilute or distort the message. The gap in high-resolution observations during September has become, for many, an unsettling analogue to the film's depiction of secrecy and selective disclosure. In Don't Look Up, officials conduct classified assessments behind closed doors while maintaining public reassurances. In the case of 3I Atlas, the absence of new imagery has inspired similar suspicions, even if the real explanations are far more mundane. The differences, however, are crucial. The fictional comet was a world killer, detected only months before impact, sparking an atmosphere of frantic urgency. 3I Atlas, by contrast, has been observed for over a year. Its trajectory is secure, its closest approach confirmed by independent teams at a harmless 1.8 astronomical units on December 19th further than Earth is from the Sun. No scientific model, no matter how exotic, suggests any risk of collision, and yet the psychological dynamics portrayed in the film map neatly onto current reality. Social media teems with competing theories, from sober natural explanations to wild speculation about alien reconnaissance. The same polarization between scientific authority and populist skepticism played for satire on screen. now unfolds across digital platforms in earnest. Even the film's critique of media sensationalism finds parallels in today's coverage. Headlines about near-miss asteroids and mystery interstellar visitors generate clicks and shares, but often at the cost of clarity, drowning out the sober assessments of astronomers whose work shows the object poses no danger. Thus, while 3I Atlas will not destroy the Earth, its presence in our skies has revealed something else, a mirror of our cultural anxieties. It shows how fragile the relationship is between discovery and trust, between data and narrative, between science and the stories we tell ourselves when the cosmos confronts us with the unknown. The film showed how legitimate scientific concerns become distorted when filtered through political and economic interests that prize short-term advantage over long-term survival. In its satire, every revelation about the comet became material to be spun, monetized, or reframed, until the truth was nearly unrecognizable. The 3I Atlas debate reflects a quieter version of the same dynamic. Scientific questions about coma expansion, tail geometry, and polarization anomalies are being interpreted through cultural frameworks shaped as much by secrecy concerns and media tropes about alien contact as by sober analysis of data. One of Don't Look Up's most prescient insights was its portrayal of how extraordinary events can be normalized by repetition and media saturation. What begins as shocking gradually becomes background noise, competing for attention with gossip and spectacle until urgency fades. 3I Atlas faces a similar risk. Initial fascination with its green coma, anti-tail, and anomalous brightness may give way to indifference, especially once superior conjunction removes it from immediate visibility. An interstellar visitor could quietly transform into just another space story, stripped of its significance by distraction and fatigue. The film's central tension, expert authority versus popular skepticism, also resonates in the present moment. Its fictional astronomers struggled to defend their credibility against charismatic personalities who offered more emotionally satisfying narratives. The current discourse around 3I Atlas reveals similar fault lines: careful scientific methodology, full of caveats and uncertainties, competes with dramatic interpretations that seize the public imagination. In this climate, transparency becomes critical. To dismiss the Don't Look Up parallels as satire would be to miss their underlying warning. When institutions mishandle information, even unintentionally, they erode the trust essential for collective response. The absence of new high-resolution images during September, paired with the inconvenient timing of superior conjunction, creates a vacuum that speculation rushes to fill. Operational constraints offer mundane explanations, but the pattern resembles the kind of selective disclosure dramatized in the film. In both cases, what matters is not only the reality of the threat, or in 3I Atlas's case, its lack of threat, but how the flow of information shapes public perception. The movie also captured a subtler danger: public fatalism and numbness. In its final act, the comet's inevitability became a backdrop for denial, distraction, and resignation. Today, frequent headlines about near-Earth asteroids and cometary visitors risk producing a similar desensitization. Many now treat such discoveries as routine curiosities rather than as windows into the dynamics of our cosmic environment. What should inspire reflection and curiosity becomes entertainment content, stripped of gravity by overexposure. Ultimately, Don't Look Up argued that humanity's greatest vulnerability lies not in external threats, but in our inability to process complex realities and act collectively across timescales longer than an election cycle or financial quarter. The Three-Eye Atlas situation tests the same fragility. Though without the existential stakes of a planet killer, the film ended in catastrophe because institutions failed to maintain credibility and communicate honestly. The present moment offers an opportunity to prove that science, governance, and media can do better. The challenge lies in balance, transparency without hysteria, caution without silence. Public confidence erodes quickly when institutions appear to prioritize political calculation over truth, as Three-Eye Atlas approaches conjunction and eventual reappearance. The handling of information will serve as a real-world test of whether the dysfunctional patterns satirized in Don't Look Up are inevitable features of human society, or failures we can choose to avoid. The film's most enduring message was that extraordinary challenges demand extraordinary cooperation and candor across institutional boundaries. Climate change, pandemics, and even the prospect of first contact all fit this category. While Don't Look Up focused on dysfunction in the face of certain destruction, Three-Eye Atlas poses a subtler but equally profound challenge. It does not threaten annihilation, but it could reshape our understanding of planetary science, interstellar space, or even intelligence beyond Earth. Such transformations, though less dramatic than apocalypse, may prove just as world-altering in the long run. Part 12. Doomsday Speculations. The scenarios that the human imagination spins around Three-Eye Atlas are not predictions, but thought experiments. The kind of possibilities that live in the shadow between wonder and fear. For a moment, one might imagine that the nucleus is not the modest fragment of ice and dust suggested by Hubble's measurements, but something larger, a hidden reservoir of volatile material that could explain the unruly brightening and the swollen coma. Yet every careful observation, every photon counted by Earth and space telescopes argues against that possibility, converging on the picture of a body only a few kilometers across. Another vision follows, the comet breaking apart during its close brush with Mars. Tidal stresses prying it open, sending cascades of fresh material into space and altering its luminous envelope overnight. Comets do sometimes fracture in this way, and if Three-Eye Atlas did, the effect would be spectacular. But the truth is that modern astrometry is so precise that any real shift in trajectory or outflow would already have been recorded, its fingerprints etched into the data. Still, doubt creeps in. What if the path itself is not as secure as the charts suggest? What if unseen forces are nudging the comet, bending its course with a subtlety our instruments cannot yet detect? The allure of such an idea is undeniable. But orbital mechanics is unforgivingly exact, and the thousands of measurements already made leave little room for invisible hands. And then, at the far edge of speculation, the imagination conjures something stranger still. A comet that is not merely a comet, but a carrier releasing smaller scouts. Devices that fall into our skies disguised as natural meteoroids. The logistics of such a scheme would border on the impossible timing, control, the need for miniaturized systems of astonishing sophistication, but the thought lingers, if only because it fits so neatly with the story the human mind longs to tell. Yet even here, reality intrudes. Global meteor networks would catch the pattern of such intrusions instantly. And so far, the skies remain ordinary in their chaos. Could the cluster of asteroids that slipped past Earth in mid-September really have been something more deliberate than chance alignments of stone and ice? To those inclined towards suspicion, their timing alongside the strangest behavior of 3I Atlas seemed almost theatrical, as though reconnaissance probes were filing through our skies under the guise of natural objects. Yet when set against the long record of celestial mechanics, the explanation is more ordinary. Close approaches occur throughout the year, usually unremarked upon, except by the astronomers who track them. What made September stand out was not a sudden increase in traffic, but the convergence of better detection systems, heightened public awareness, and the uncanny presence of an interstellar comet whose green glow had already captured the world's imagination. Still, the theatre of the skies was undeniable, made even more dramatic by the sun itself. Solar maximum, the high-energy peak of our star's 11-year cycle, flooded the heliosphere with heightened particle radiation and coronal mass ejections. For a comet like 3I Atlas, these conditions were a crucible. Sudden bursts of solar wind can tear an ion tail in two, disconnecting it like a flag ripped from its pole, or pump brightness upward in jolts that seem inexplicable to casual eyes. Such episodes can look alien, yet they obey the same physics that governs auroras on Earth and plasma arcs on the Sun. Engineers design our satellites and power grids to weather these storms, and nothing in these interactions implies danger beyond the usual choreography of space weather. If a true hazard ever emerged, the world would not be left guessing. Networks already exist, finely tuned to identify and broadcast potential threats. The Minor Planet Center collects data from observatories across the globe. The Jet Propulsion Laboratory in California maintains the definitive calculations of near-Earth trajectories, and the European Space Agency provides independent confirmation. These institutions work in concert to ensure that if an object truly endangered Earth, word would travel swiftly through official channels rather than through rumor. But reason alone does not calm the imagination. Humans are wired to search for patterns, to anticipate threats in shadows and omens in the sky. When an object from another star defies familiar expectations, that instinct intensifies, weaving visions of doomsday from the threads of uncertainty. Yet each line of evidence still points towards safety. The path of 3I Atlas keeps it millions of kilometers from every planet. Its chemical oddities stretch, but do not break natural laws. And its evolving behavior, though dramatic, remains consistent with processes seen in comets forged under unfamiliar conditions. The real challenge is not survival but understanding. This icy wanderer offers a once-in-a-generation chance to study matter from another sun, a piece of cosmic history that carries within it the story of planetary formation beyond our own system. Whatever conclusion science ultimately reaches, whether it reveals only new twists of cometary physics or hints at something far more extraordinary. 3I Atlas is a gift of knowledge. It reminds us that the universe still holds secrets capable of unsettling our reason while igniting our wonder, and that even without catastrophe, the encounter itself may change how we imagine our place in the galaxy. Part 13. Final warning. The alien look of Atlas intensifies as 3I Atlas races toward its October rendezvous with the inner solar system Three pillars of strangeness continue to set this visitor apart from every other comet ever studied, creating a combination of features that feels almost engineered to capture attention and to challenge the very foundations of comet science. The first is the rapid brightening anomaly that broke away from predicted light curves in mid-September. Brightness forecasts for comets are usually among the most reliable tools in astronomy, grounded in decades of careful observation and well-tested physics describing how ice sublimates under solar heat. Yet 3I Atlas defied the models. The deviation was neither minor nor subtle. Amateur astronomers around the globe reported the comet shining brighter than their charts predicted. While even professional software underestimated its glow, observatories scrambled to revise their models, forced to admit that something fundamental about the behavior of interstellar ice had eluded them. The second pillar involves the sheer scale of its atmosphere and its chemistry. The carbon dioxide-dominated coma now extends hundreds of thousands of kilometers, a level of activity astonishing for a nucleus, measured in only a few kilometers. James Webb's spectroscopic data revealed chemical ratios alien to the comets of our own solar system. The dominance of carbon dioxide suggests formation under conditions colder and stranger than any that shaped local objects. Combined with the speed of its expansion, this chemistry implies either exotic compositions or sublimation processes operating far more efficiently than current cometary models allow. The third and most compelling pillar lies in its light polarization studies, which probe how dust scatters sunlight based on its size, shape, and surface texture, have returned values no natural object has ever shown. A negative polarization dip of nearly 2.7% at a phase angle of about 7 degrees, with an inversion point around 17 degrees, lies far outside the behavior of known cometary dust. These signatures point toward dust grains formed under conditions unknown in the solar system, or perhaps made of substances unlike any found in its natural inventory. Taken together, anomalous brightening, extraordinary atmospheric expansion, unprecedented polarization, the data create a profile that goes well beyond casual impressions. Add to this the eerie green fluorescence and the sunward antitail, and 3I Atlas becomes not just unusual, but visually and physically alien. For all its strangeness, its trajectory remains safe. Orbital solutions confirm that the comet will keep its distance from Earth, with its closest pass on December 19th carrying it no nearer than 1.8 astronomical units, well beyond any danger. Its October 3rd encounter with Mars, while close in astronomical terms, offers scientists a golden opportunity rather than a hazard. Yet the observational timeline itself has become part of the story. Since July, when Hubble delivered its last high-resolution images, and August 6th, when Webb revealed the comet's peculiar chemistry, no fresh space telescope imagery has appeared in public archives. The last detailed professional photograph remains Gemini South's August 27th capture, leaving September's dramatic changes documented only by amateurs, whose images fill social media but lack the precision of calibrated instruments. Now, as the calendar slides toward late October, the geometry of the solar system conspires to make matters worse. Superior conjunction will carry 3I Atlas behind the Sun from Earth's perspective, just as it reaches its most active phase near perihelion. The timing is an accident of orbital mechanics. but one that feeds both genuine operational challenges and suspicions of deliberate suppression. For astronomers, it is a frustrating blind spot. For conspiracy theorists, the perfect cover. Still, the blackout will not be total. Spacecraft scattered across the solar system, Mars orbiters, solar observatories, and probes with alternative vantage points will continue to watch, ensuring that the comet remains under scrutiny even when Earth-bound eyes go dark. The Mars flyby of October 3rd may represent the last clear window for high-quality imaging before 3I Atlas slips behind the sun's glare, making these observations invaluable for probing the comet's true character. What is at stake is more than data points and orbital models. How the scientific community manages this moment, what it reveals, what it withholds, how quickly it shares. Results will establish precedents for how humanity responds when confronted with astronomical discoveries that strain the limits of understanding. The case of 3I Atlas has already reshaped the dialogue between science and society. Its combination of anomalous brightening, extraordinary atmospheric expansion, and unprecedented polarization values has forced astronomers to question models long treated as reliable. At the same time, the curious gaps in high-resolution data and the comet's increasingly dramatic appearance have created conditions that test public trust in scientific authority. In the absence of steady, transparent communication, speculation about alien intelligence and reconnaissance missions has flourished, proving how quickly extraordinary observations can ignite the collective imagination. The sober assessment remains that natural explanations, however stretched, still hold the upper hand. Exotic volatile mixtures, unfamiliar internal structures, or formation environments colder and stranger than those in our solar system could plausibly explain the comet's behavior without invoking technology. Yet the accumulating anomalies have pushed those natural frameworks to their breaking point. 3I Atlas seems to operate at the very frontier of current theory, demanding either radical extensions of known physics or the unsettling consideration of alternatives that alter humanity's conception of its place in the cosmos. What confronts us is a stark dichotomy. Either 3I Atlas is the most unusual natural body ever detected from another star system, or it is the first credible evidence that intelligence exists on galactic scales and possesses the means to send probes across light-year gulfs. Each new observation brings us closer to resolution. In the weeks ahead, the comet will either settle into the textbooks as a rare but natural marvel of interstellar chemistry, or it will mark the moment when humanity realized it was under observation from beyond the stars. The nearer 3I Atlas moves toward the sun, the more alien it appears. Whether that alien quality is the result of genuine otherworldly design or of natural processes unfolding under conditions unfamiliar to earthly science remains the central question of modern astronomy. When the comet re-emerges from Superior Conjunction in late November, the world will have its answer. Either 3I Atlas will reveal itself as the most exotic natural phenomenon in the history of cometary observation, or it will stand as humanity's first glimpse of galactic intelligence at work. In either case, the outcome will redefine what we know about physics, about life, and about our place in the universe, securing 3I Atlas a place among the most significant objects ever witnessed in Earth's skies.